it's now my pleasure to introduce Derek Lowe. I think you probably all of you know them. Derek was the first one that I'm aware of who was a blogger. At that time, I didn't even really know what a blogger is, but Derek did it, and he did it for quite some time, coming up with all kind of interesting topics, shedding light on what we are doing, but also with some critical remarks that gave pause to us to think about why it is we are doing it, what it is we are doing, and what are the limits of what is going on here now. Derek, as you probably also know, is also the director in exploratory chemical biology at Novartis. Derek, the floor is yours. We all look forward to your presentation.
Thank you very much for that introduction. I'm really glad to have the invitation to come here and speak on this topic, because it's something that's kind of near to my heart in a way. When I first joined the industry back in 1989, this was in the first flush of enthusiasm for automated and computational approaches. And in fact, the company I was working for at that time, who are long gone in the way of the pharmaceutical companies, they've been eaten by another company that was eaten by another company. But at any rate, they cleared out a room and filled it with state-of-the-art late 1980s hardware. And this is the sort of thing that you would have to go to some kind of technology museum to see now. Evans and Sutherland workstations, that sort of thing. And they had, there's some people who recognize those and are laughing. They put a sign over the door that said CADD, and no one knew what that meant. And it was explained that this was computer-aided drug discovery. So the medicinal chemists across the hall were a little unsure about this principle, and they hand letters aside and put it over their labs that said BADD, brain-assisted drug discovery. Well, there have been several cycles of enthusiasm for this kind of thing, as those of you who have been in industry for a while and in the field for a while know. And we are currently in perhaps the biggest of them all with the AI and ML approaches. And that is my topic, is what is the reality of this field and what are people expecting from it? So machines and humans have been at this, together for quite a while, since the beginning of civilization, more or less, if you count, making arrowheads and things like that, and I do, as technology. And during this time, it started out with physical labor, things that were too heavy for us to lift, or things that were too repetitive for us to put up with as human beings. And machines are great for that. And now it is mental labor. The repetitive aspect is still there, things that we can't stand to do over and over for days or weeks on end. But we're also looking for data sets that are too large for us to work through, and patterns that are too subtle for us to see with our unaided intelligence. Now, this also has been coming on for a while, and if you dig back in old newspapers and magazines, you find a lot of stuff like this. This is the traditional worry. This is from 1931, and the question was, is man doomed by the machine age? You still have people asking this. There are still people wondering, is AI going to take my job? That was easier to answer no before some of the large language models, and it's kind of terrifying to think of how many human jobs are actually perhaps substitutable by a large language model. My own feeling, as someone who does writing in the side, the day job is of course in pharma, but as someone who writes on the side, I think if you cannot write better than an LLM, you need to learn to write better. But they are very helpful. We're going to get back to those guys in a moment. But the traditional function of machines are to release us from drudgery. Now here's a lab from probably, I don't know, late 1940s, early 1950s. And as a chemist myself, I can tell you that what these people were spending all day doing is, they are tasks that no chemist of a modern era would put up with for 5 minutes. This practically, I don't even know if that's commercial glassware back there. People were molding their own corks and sealing them with wax. People were doing everything by hand But that was the cutting edge at the time, and that's what people got done. 30, 40, 50 years from now, people will be looking at what we're doing in the labs right now and go, oh my God, those poor people. I can't believe they were doing it that way. But the question is, how much of what we're doing is drudgery? And how much of it is going to look like drudgery as time goes on? Well, experimentation, as we all know, is actually work. There's experimental design, which takes a great deal of time and effort if you're going to do it right. Measure twice and cut once really is the rule. Setting things up and actually running the experiment is non-trivial too. And that's where the automation comes in with a great deal of help. I was sitting around a couple of weeks ago watching an echo machine dispense a lot of, these are 1386 well plates, and watching them dispense mixtures into that and thinking how long it would have taken in the old days to do this. It's just fantastic. But you are the one who has to come up with the programming for the echo and design what you want it to do. Because my law of automation is that anything that can work by itself can screw up by itself. And it will screw up more thoroughly, more completely than you could ever screw anything up by hand. Collecting and curating the data, that's a job all by itself, but interpretation, what you do with all that data, that strains us to our limits as human beings these days. And sometimes it may actually well be beyond human ability. But as a medicinal chemist, that's where I've spent most of my career, let me bring this back to earth by talking about a medicinal chemist's problems. And this is the way I see them. I don't think they've changed over the years. You have the problems that are right in front of you. What compound should I make next? How should I make that compound? That is the day-to-day life of a bench medicinal chemist. What to do next? Should I put a methyl on here? Should I flip a chiral center? Should I substitute that carbon for a nitrogen? What is the SAR telling me? How do I do that anyway? Beyond that, though, there are some larger problems. How potent and selective do the compounds actually need to be on this project? How do we know when we've made things that are good enough and we can all stop? That's a very difficult question to answer. How do we balance those with the PK and absorption metabolism type properties that we're going to need for dosing? What counter screens? What tox assays? What things do we need to worry about? Do we have hERG problems? Do we have solubility problems? Do we have clearance problems? These are the larger issues, and of course, after you've been doing medchem for a little while, you find that you're thinking about these as much or more as you're thinking about what compound you should make next. But there's an even bigger problem that a lot of us actually don't think about very much, and I think that's almost deliberate because we don't like thinking about this larger problem. And that is, what project should I even be working on? Should we be doing this target at all? Should we be in this disease area at all? Now that's a job, of course, for the higher ups in the company, all your directors and division heads and executive whatevers. But that's a really crucial question, and a lot of smaller companies have actually used up all their money and disappeared because they weren't able to answer that question well enough. Okay, look at those questions and think about which ones are going to be helped out by AI and machine learning. You will find that there is an almost perfectly inverse relationship between how much machine learning can do for you and how important the question is. ML can help you out with suggesting compounds that you might make next. It'll help you out with how well these ideas of yours might bind to your protein target. How should I make them? We're getting better and better at retrosynthesis type assistance computationally, although it's harder than I thought a few years ago. The organic chemistry literature is actually a gigantic steaming pile, and there's a lot of stuff in it that shouldn't be there, and there are a lot of weird biases that are shot through it that make the problem more difficult, but it's a doable problem. But as you go up to these higher order questions, it gets harder and harder because Of course, for machine learning, you need data, piles of data, huge amounts of it, beautifully curated. Where are the piles of data that will help you decide if this is a good project to work on or not? Where do you find those things? We're going to come back to that topic. I think that there's actually a conservation law at work in machine learning. Machine learning, this is just my take on it, and I will be happy to be contradicted. I do not think it creates any knowledge whatsoever. What you find in it is what was in there already. It can better reveal knowledge that was already in your data set, or put it into a more useful form, and I'd say that's what something like AlphaFold or RosettaFold does. But it cannot make discoveries that were not inherent in the data. It will just help you to realize that they were there and help you to realize ways to attack these problems. And I'm not trying to put ML down. I love machine learning, but I think it's good for us to be realistic about it and know what it is supposed to be doing for us. So there's a thought experiment that came along in the early 80s that if any of you have had philosophy courses, you may have come across. John Searle's Chinese room experiment. And back in the early 80s, Searle said, you know, if you were to lock me up in a room with a gigantic set of rule books and heuristics and flowcharts to deal with the Chinese language, as he pointed out, he did not know anything about spoken or written Chinese. But he said, if you gave me, in theory, the most gigantic set of rules and heuristics and flowcharts about Chinese, a native Chinese speaker could send in a question and I would look it up. Okay, this has these two little marks that go like this, and below it there's one squiggle, and then one that slashes down to the left. Dig, 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 root, 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 flip, flip, flip. He could gradually work out what an appropriate response to this might be and send it out. And if you just had enough pizza and Mountain Dew or whatever in there and enough years of life on that diet, you could fool the native Chinese speaker outside the room into thinking that, yes, there is a native Chinese speaker in here. But as he pointed out, I myself, he said, know nothing of Chinese. I am just in here flipping pages and making marks on paper and sending it out. Well, if this reminds you of how AlphaFold does protein structures, well, it should. This is how a machine learning program like AlphaFold or RosettaFold does protein structures. It has come up with a gigantic rule book of when there is a proline followed by a this, followed by an arg, followed by a that, it tends to make a curl that usually looks like that unless there's another thing over here. But if not this, then that, then try that, and etc. That's all it is. There is no understanding in there whatsoever. And that brings you up to this topic of answers versus reasons. When you think of all the time that we spent, and are still spending, but especially that we spent trying to do protein structure from first physical principles, trying to learn more about hydrogen bonding, about torsional strain, about steric hindrance, pi-pi interactions, all that stuff. Everyone, most everyone, was trying to model proteins from first principles like that and work their way up. Well, as I say here, if that protein structure problem was sent to us by God in order to force us to learn about all these thermodynamics and physiochemical principles, well, we cheated on the exam. We did. We shortcutted it and went straight to the answer. So we may find out that God is very disappointed in us if that was the idea. But I'm not disappointed in us. I'm glad we have the answers. But this teaches us that fundamental understanding is not necessarily a requirement to get those answers. And that's a bit of an unnerving thought. We still, I mean, if you'd showed me what AlphaFold could do, if you'd showed me that back in like 1995, I would say, my gosh, we must have really figured out a lot of fundamental stuff about steric hindrance and strain and all these things, pi-pi. No, we didn't. We know more about it, but we don't know enough to do protein structure from those first principles. So this gets to a very large topic in science, and that is reductionism. We have made a lot of headway over the decades by digging into the finer and finer and finer details. And there are always finer details. You guys know what it's like. You work and you work and you work and you finally get this door to open up, and it opens up into an extremely long corridor full of other doors. And then you pick one of those and you work and work and work, and you finally open that up, and it opens up into another corridor full of doors. And that's kept us all busy for a long time, and it's going to keep us busy for a long time to come. But reductionism is only one tool in the box. Let me demonstrate. That. What the heck is that? Well, a bunch of colored blobs. If we're going to analyze it through real scientific reductionism, we could slap an XY grid on the thing and say, okay, there may be some relation to the different colors here on the XY grid. Some of them may occur more in some quadrants than others. The size, the shape of these blobs, their various hues and tonal values. Let's just work up a whole bunch of different plots and see if we can find some relationships in here, and see if we can find out what this thing is about and what it's trying to tell us. You will not. There is no way that you can analyze this thing in that method and at that level of detail and figure out what it is, because here's what it is. It is a tiny piece in the shadow of this woman's dress in that Seurat Impressionist painting, La Grande Jatte. That's what it is, just blown up. And there are the single little pointillist dots that he put in to fill up that gigantic canvas. And my contention is, in the same way that you cannot go from that small-scale picture with all the details, you cannot go from that on the left to that on the right. It also means that you cannot go from this, the huge, massive pile of fundamental detail in biochemistry, to that, a living cell. There is no path to do that. You have to go past reductionism and start putting things together into systems, which is very, very difficult. Well, fortunately, we have some parts of it that are a little bit easier to get a handle on. Consider protein sequences have only about 20 words in them, the natural amino acids. Nucleotides have even fewer. You've only got 4, which 4 depending on which side of it the fence you're working on. But by themselves, they actually encode a lot about structure, and that's why AlphaFold works, that you can go from sequence to structure, because we know that prolines introduce this kind of turn, and et cetera, and phenylalanines tend to stack together, all these things. We also know that these structures say a lot about function, which is how we can annotate and say, aha, look at that thing. You've got a serine over here, and you've got these histidines over here. That looks like it must be a hydrolase, because these pockets with the histidines are there to activate the carbonyl, and that serine looks like an active site serine, et cetera. So you can learn a lot just from sequence. Now this, computationally, is a staggeringly beautiful example of an evolutionary optimization of Shannon entropy. If any of you are into data science and information, this is communication across a noisy channel. And because, believe me, replication over billions of years is a very noisy channel, but this is a beautiful job of optimizing the information that's being transmitted. And this is what allows us to do the kinds of things that we do in molecular biology and chemical biology, is the fact that this system is so beautifully compressed and complicated. Well, let's switch to Spanish literature. Ha, that woke you up. Jorge Luis Borges, The Library of Babel. If any of you have read this short story of his, the universe, which others call the library, is how it starts out. It's a weird thought experiment, like a lot of Borges, and in this one, it describes a gigantic library that stretches off into the distance farther than the eye can see, in all directions, full of hexagonal rooms that are lined with shelves, and every shelf is full of 400-page books. If you go to the shelf and take off a book, it looks random. It's full of gibberish. And that is because the librarians who inhabit it have gradually realized that it is the set of all 400-page books that can exist with the 26 English characters and 2 punctuation marks. All of them. every combination, everything that can be written down is there. That means it's not infinite. It means it's very, very, very large, much larger than the observable universe. The number of books is larger than the number of quarks in the universe. It's huge, but it's not infinite. But everything is there. The detailed history of your life, the detailed history of your life with one word misspelled, the absolute false, scurrilous, insulting in history of your life, the history of your life written phonetically in every other human language. As W.V. Quine pointed out, you only really need 2 letters because everything that can be said in binary, so why not? Well, that is Borges' thought experiment, but we have something that's a little similar to that. As Daniel Dennett pointed out, we have Mendel's library instead of Borges. This is the library of protein sequences. And if you put a limit on the size of a protein, then that is also not an infinite set. It's just very, very large. But Mendel's library has been curated by evolution, brutally curated, because it's much, much smaller than the number of possible sequences. These are the ones that actually have some sort of use in living systems. And we're starting to add books to this library because we are now starting to be able to design functional proteins ourselves with the sort of work you see at David Baker's lab and others. Well, what about then natural human language? And that's where we get to LLMs. Chatbot inputs and outputs are all part of the Library of Babel. That's because everything is part of the Library of Babel. But the training set for a chatbot is not curated by natural selection like the protein universe library of Mendel. It's curated by us, by humans, by what we have written down. That is why currently some of the large AI companies are in a great deal of hot water over whether or not they have systematically and totally violated every copyright law in humanity by shoveling every single text they could possibly get their hands on into the data sets for chatbots. And it's basically what is proven grammatical and maybe even useful. Now, the outputs of chatbots are another thing entirely. The examples of outputs from large language models leading people astray are too numerous to mention. That one up in the upper right is one I did myself. Google's AI confidently told me that the French word for popover is, quote, Yorkshire pudding, which I found fascinating. The main difference between a dressing and a sauce is their purpose. A dressing is used to protect wounds, and a sauce is used to add flavor, etc., etc., etc. And of course, the LLM people call these hallucinations, and they promise us that they're going to be getting rid of these. They will not. I think the hallucinations are an intrinsic property of large language models. And if you got rid of them, you would have a natural language. And you would have a natural language with knowledge and reasoning and understanding behind it, which, again, my opinion, is the one thing that large language models do not have and will not have. Now, people have tried to deal with this. There's retrieval augmented generation, where you try to purify your source material and not dump in every single book or internet comment in the world. And that can work out pretty well. This is, for example, Open Evidence, which is a little phone app that a lot of physicians use to kind of keep up with the medical literature and come up with useful suggestions and the like, because the medical literature is, of course, too big for a human to keep up with. Open Evidence is pretty good, and as their publicity shows in the upper right, they had the lowest error rate in history if you feed it into the medical licensing exam in the US. But if you look into it a little more closely, and that's what those links at the bottom have, it does make quite a few mistakes. And as long as you're sticking with things that are well-trodden and come up a lot in clinical practice, it does pretty well. But as you go off into the areas that you're less likely to know something about, which is to say the areas in which you are more likely to consult your Open Evidence AI friend, that is where it starts to go off the rails. Now, coding, another big topic in AI and ML. Coding is more complex than protein sequences, but less complicated than a human natural language. So it's a nice place to see how things are going. This, and I have the link for this, this study shows that the code editing benchmark, the percent of tasks completed correctly, has not changed all that much over the last couple of years. And that includes the latest GPT version, which was supposed to be a gigantic leap forward in coding ability. According to them, it is not. Now, this is either very impressive. If you didn't know about these things writing code, it's not bad. Or it's not as high as you might have thought if you just read the press releases, which are talking about how no human's going to bother to write code. 10 minutes from now, we'll have all this thing figured out. Apparently not. Well, there's coding for you. Let's pick another one that's also not a natural language but can express great complexity, mathematics. The latest GPT release is claimed, quote, to be more adept at mathematical reasoning. But this was a good preprint from a team at Apple showing that just switching the numerical values around in the test questions degrades it a bit. Now, to be fair, it degrades the other chatbots a lot more. So the latest version is a lot more robust for that. But if you introduce extraneous phrases in your prompts, things break down very quickly. So if you say, if John has 10 apples and Mary has 4 apples, who has more apples? It will actually tell you, yes, John has more apples. But if you say, John has, I don't know, 10 little tiny green apples, and Mary has 4 great big lovely red delicious apples, who has more apples? It gets the answer wrong. Because it is not reasoning. It is just mimicking what reasoning looks like from its data set. It's doing a pretty good job of it. But as I mentioned on one of the earlier slides, we are used as humans to assuming that anything that can use language this well is actually intelligent and has agency and has intention and has intelligence behind it. We are being fooled by that. Now, I don't know if future generations are going to be fooled more thoroughly or less thoroughly by this as time goes on and they get more used to it. And there's been another claim that as you make the data size of these things higher, you get emergent properties, sudden increases in their capability. But that doesn't seem to hold up either. It appears to be an artifact of the metrics. If you use different systems to measure them, these amazing emergent leaps forward disappear. Exactly, not a fundamental property of the model. Well, I'm going to bring this back around to what we like to do, but I'm going to do it via Ludwig Wittgenstein. All right, woke you up again. I like this talk for that. It really kind of throws people, and it kind of throws me, actually, when I give it. Wittgenstein said that anything that can be said clearly, which is a very comforting thought, but note that that is actually phrased in the form of a qualifier, anything that can be said. And Wittgenstein famously said that in any language there are things that cannot be said. As he put it at the very last sentence he wrote as a philosopher, wovon man nicht sprechen kann, darüber muss man schweigen. What we cannot speak of, we must pass by in silence. And he did. That was the last philosophical thing that he ever put to print or in speech. That means that there are, in fact, things that you cannot talk about. What does that mean for what we're using? It means that an LLM trained on code can write, sort of, code in what can be a useful way, but it cannot pick the most computationally efficient design for your project because it doesn't know what your project is, and it doesn't know what a project is. Similarly, the language of protein sequence tells you a lot about proteins. It tells you a lot about their structure. That's how, something like AlphaFold can work. And it even tells you a fair amount about function, but it cannot tell you about what their role in human disease is. It cannot tell you about which one of these proteins might make the best target for you and your company to work on. These are unsayable in the language it knows. It doesn't know what you're talking about. So the largest questions for now, I think, are beyond reach of ML. What does that mean for us? It means we have to pick our topics carefully. We need to pick bounded problems that have a lot of very good data. And it also means that the common approaches that have been developed for messing with text and human language and messing around with images, generating, bizarre images via prompts, these are almost certainly not appropriate to the kinds of problems that people in an audience like this want to do. We need to come up with others, and we need to be very careful in the tools that we're using. And very careful about the problems that we're using them to. Well-bounded fields with well-curated data. Make sure that your machine language problem is in a defined space where meaningful data are available, and that's positive data and negative data. We, and I mean scientists, and we especially chemists, have done ourselves a vast disservice by not publishing negative data over the years. When we get negative data, we follow the principle of if at first you don't succeed, destroy all evidence that you even tried. We don't put it anywhere, and we are paying the price for it now, because we would be a lot further along in that retrosynthesis literature work if we had reliable negative data, but we don't. We have negative data that's not reliable too, because a lot of experiments that didn't work because someone messed up. They let a little water in there, or a little oxygen, not because the reaction's fundamentally unsound. So make sure that you're working in a space where meaningful data are available. Get as much of that data together as possible. Curate it obsessively. Garbage in, garbage out has always been the rule of computation ever since World War II and Alan Turing. We have a garbage in, garbage out situation that is almost beyond human comprehension in its strength and its terrifying ability. So you must make sure that your data are beautiful, and make sure that the answers that you're looking for are actually things that are sayable in the first place, in the system that you're working in. Make sure this is a question that can even be answered. The machines will give you an answer. Every time, they will give you answers in the same way that they will tell you that the French word for popover is Yorkshire pudding. They will give you an answer. And your job is to make sure that you are forcing them to give you answers that will be useful and believable. So this is where we come in. This is getting back to physical automation. This is Steve Lay, an excellent organic chemist in London. Machines are never fully able to mimic or automate the abilities of an innovative bench chemist, but they help by generating more time to think and to design new processes. We'd better be prepared to use that time wisely. I had a talk on AI and ML I used to give several years ago, and I pointed out that this was going to force us to work at higher levels all the time. I had that drudgery slide in there, and I pointed out that a lot of the things we're doing now are going to be seen as drudgery in another 10, 20, 30 years. We will be working on higher level problems. We will be trying to solve those problems like, what project should I even be working on, and things like that. That's still going to be left to us, the humans. So you also have to, as a person, be ready to work on those higher level problems and be ready to turn over the grunt work to the machines and realize that the definition of grunt work is constantly evolving and creeping up on you. General intelligence, I think, is not the issue. There's a lot of talk about AGI in the field, and I'm not paying attention to much of it. I have to agree with Robert Heinlein. Specialization is for insects and for machines. Humans, we are the ones who synthesize these things, who exercise our own judgment on top of them. We're going to be working at this higher level, doing the things that machines can't do. In fact, that's probably going to be a condition of employment, that you do things that machines can't do. Synthesizing knowledge, exercising judgment, making sure you're using the right tools for the right jobs. And because one of the most guaranteed unsayable things for any machine model is to evaluate where it itself should best be used. That is definitely up to us. So we have the hard way. Remember, Einstein said a theory should be as simple as possible, but not any simpler. Well, we have focused on breaking drug discovery down into simple steps, reductionism, and it made sense scientifically, financially, but we're dealing with systems now that are more than just the sums of their parts. We have to be ready to get rid of reductionism and apply the kinds of thinkings that only humans can do, while using the absolute best judgment we have about these incredible machine techniques that we are using now, that we're going to be hearing about for the rest of the day. We have to keep our heads up, look around, and think very hard, because the machine learning is not here to do our thinking for us. Machine learning is here to make us think even better thoughts. Thank you.